Hello everyone, my name is Pablo Di Giulio. Today I will show you the implementation of the floating point multiplication using VHDL. This project was developed for reprogramable system. As we know, the IEEE format fixed point floating point format is composed by three parts. The first part is the sign, the next part is the exponent, and the last part is the mantis. In order to perform the multiplication, we could split this problem in three parts. The first part is the sign. The sign is just only a simple XOR between the sign of the two operands. The second part is the multiplication of the mantisas. We must take into account that the format hides the most significant bit of the mantisa, so we must take into account that bit into the multiplication. The multiplication is a multiplication of 24 bits times 24 bits, so the result will be 48 bits, but we must take into account that we concatenate a 1 like a most significant bit, so we must take into account the normalization of that value. The normalization of that value is indicated by the most significant bit of the result of the multiplication, and if this value is 1, we must increase 1 the addition of the two exponent part. I will show you the implementation in VHDL. Well, this implementation was taking into account some constraint due the assignment. One of the constraints was that the multiplication of the mantisa must be a sequential multiplication instead to use a parallel multiplication. We implemented both parts. The multiplication part was implemented, the parallel multiplication was implemented using the fourth generation in order to generate a cascade multiplication scheme, and the sequential multiplication is the next one. I will show you the code of VHDL, the code in Quartus. So we can see we have the top level of the solution. Inside of the top level of the solution we have the floating point unit and the two ROM memory where are the data that we are going to use to multiply, that we are going to use to stimulate the floating point unit. The floating point unit is composed by a final state machine that controls all the data path of the information inside of the floating point unit. Then we have the exponential part, that is just only an addition of the two exponential minus or subtracting the bias and taking into account if the multiplication generates a normalization or not, a rounding or not. So we also have a unit that is in charge to check exceptions, like for example -0, 0, or not a number. Well, now we are going to see the floating point multiplication that as I said, this multiplication was implemented using a sequential multiplication. The floating point, this is just only the multiplication of the mantisa. It's composed by two, but one final state machine and one data path. Inside of the state machine we have the different state of the state machine, that is reset, init, load, calc, done, and finish. And in the data path we have all the components that perform the movement of the data. I will show you the scheme or the architecture that we use to implement the sequential multiplication, integer multiplication. As we can see here, we have a huge adder. As we know, the multiplication of two numbers is a multiplication and addition, a multiplication and addition. So we have a huge adder that taking into account one operand from the one register, and it could be also be 0. The selection of the multiplexer depends of the other operand. As we can see here, we have operand A and operand B. The shifting of the data is performing through this path, yeah. So we are shifting the data. One time that we go out from the register, we take part of this register and we concatenate with 0, performing the shifting. So we execute this loop as much as the counter says. So in our case, the multiplication is 24 bits times 24 bits, so the preload down counter count from 24 till 0. So one time that we perform the multiplication, and addition, we stop and we send the signal that says that all the multiplication was performed. If we check at the top level, or at the floating point unit level, we have another state machine. This state machine controls all the flow of the information along the data path. So this state machine just only, well, I will describe this part. Is easy. When we receive the start signal from outside, from one push button, we jump to the load state. In the load state, we enable the register that we have at the beginning. If we see, this is the top level scheme. At the beginning we have 2 registers in order to latch the data. Then we jump to the checker. The checker is a unit in charge to check the exceptions. As we can see here, we have the unit here. We enable the exception unit, and in the next clock we check if there is an error. Yeah, if there is an error, we jump to the error state, or we start the multiplication. In order to start the multiplication, we send an start signal to the mantis unit in order to execute the mantis unit state machine. So as we can see here, we wait for the ready signal from the mantis unit that says okay, we finished with the multiplication, and now, well, we are ready to push the data out. As we can see, the exponential part is just only a simple logic, combinational logic. Is an addition of 2 exponential part, and also subtracting the 127 of the byte. We can see here the final, well, in case that the checker unit or exception unit return an error, we must enable this register that latch the exception error value, so we can read this output and check what was the exception. Otherwise, we can get the value here at the output of the result of the multiplication. If we go at the top level of the solution, we'll see that we have the floating point unit, and we have also 2 ROM memories that are used to get the data in order to select the operands, yeah, that we are going to multiply. And also we have a multiplexer that could show in the board the operand A or the operand B. So this is the implementation of the multiplication using VHDL. Another important thing, these are the results for our design. Yeah, we can see that for this FPGA we just only consume less than 1% or 1% of the total logic element, and also 135 registers, so it's nothing for this FPGA. So now I will show you the functionality of how this project works.